Hello, today I'll present a tutorial of a spoof surface Plasmon Polariton transmission line. So it will be a simulation conducted on CST Microwave Studio. So these are the steps that we'll be taking. First, we're going to design the unit cell, and then I will show you how to do the simulation setup. That is, we're going to use the eigen mode of the on CST, and then we're going to use the time domain for later verification. And then thirdly, we're going to present the results, which will be mainly the dispersion diagram of the structure and and to verify we're going to present the S parameters of the whole transmission line. So this is the unit cell that we're going to be designing. It is based on an FR4 substrate where the relative permittivity is about 4.6 and the loss tangent is 0.007. So it is based on the following paper that we see in the reference. So it is actually a double-sided spoof surface plasma polarity and transmission line, meaning that we have the same structure on the top of the substrate and the bottom of the substrate. So a standard spoof surface plasma polariton line would have a ground layer instead of the same structure, but here we're going to design a double strip um, SSPP line, but the procedure is the exact same with a standard SSPP line. Just that we have a ground layer uh, at the bottom of the substrate. After simulation, this is what you should get in the table section. And you can see that there is a clear outlier here, and this is because of the simulator. Sometimes it can make mistakes. But we can discard this outlier and actually join the first point to the third point. And if you check the values here, you can see, you can see the value of the outlier at about 13.3 degrees. And we can discard it by going on post-processing and then plot data in ASCII format, and you can save it, and then we can do further processing in order to trace a clean SSPP dispersion diagram. So this is the dispersion diagram after further processing on Python, and you can see that now it's clean. There's no outliers, so this represents your SSPP dispersion. And how do we actually interpret this? Actually, before saying that, we can see that we actually also joined we have created a point with zero coordinate because of the fact that we've started the phase at 1 degrees, because in the simulator when you started at 0 degrees it makes an error, so we actually made sure to join them at 0, 0. So now how do we actually interpret this graph? You can see that the unit cell dispersion is increased. It's non-linear actually, so that means that if you want to use them for phase sensitive application, it's going to be a very narrow band, so it's not recommended to use SSPP for this case. And also you can see that there is an asymptote at around 67 gigahertz, which means that if we simulated a full structure like a transmission line, at around 67 gigahertz, you can see that their signal will not be transmitted, and this is because due to the band stop of the periodic structure. What this dispersion diagram also tells us is that we can see that compared to the dielectric light line at 4.6 of having relative permittivity of 4.6, which is represented by this line here, we can see that the effective permittivity of the SSPP mode is much more increased than the dielectric light line, which means that if we have an increased effective permittivity, that means we have also an increase in the wave number, which means that we can make now circuits that are much more compact than standard microstrip, for example. But it also tells us that it's a very strong bound mode. Okay, the SSPP mode is very bound to the surface, and it does not radiate easily into the dielectric, because you can see that when we vary the phase of the Brillouin zone, it's always the SSPP mode is always below the dielectric line. So this is a very important result, and you can see that also it presents like a TM mode like dispersion. So, and due to boundary conditions, because we only excite one conductor. And yeah, the dielectric light line is a TEM mode, and now what we can do now is actually confirm that the SSPP line that we have designed actually has a band stop at around 67 gigahertz. Here's the design transmission line. So it is composed of the unit cell repeated 11 times in a periodic manner. And what we would expect from the S21 is that we get almost all transmitted power from port 1 to port 2 until we hit 67 gigahertz. We should have like a drop in the S21. So we can check this, and we can see indeed that at around 67 gigahertz, we have a drop in the S21 response, and this is how you can interpret the dispersion diagram of our unit cell. So this concludes how to simulate an SSPP line, and thank you for watching.